Hi. I'd like to talk today about some of the things that can go wrong in science and how often they happen. First, I'd like to thank the organizers for asking me to be here. I'd like to thank you all for showing up, and I'll just get right to it because 6 minutes is just brutal. So this comes from a talk that I gave last summer. You can find it on YouTube. The broader context was how can science go wrong? How often do those things happen that make it go wrong? What can we do about it? And today I just want to focus in on a couple of things, but just the broader context is there's a lot of things that go wrong in science besides just the statistical error that we spend a lot of time trying to quantify with statistics. There can be fraud, there can be errors in statistics, experimental design errors, there can be things that happen technically that we don't understand. There can be biases in publication. I'll only talk about a couple of these things today, but the longer talk has more about all these things. I want to start by talking about a kind of analysis error that has multiple names: researcher degrees of freedom, forking paths. I'll call it harking after a paper by Kerr, hypothesizing after the results are known. This is when you start making hypotheses after you've seen the data, and as a result, you start answering questions that were proposed by the data itself. This creates a problem in terms of how much type 1 error your analysis will have. And I'll show you an example of that in a second. A lot of us in ecology and evolution have admitted to doing harking at least once. Here's a hypothetical example. This happens all the time, but I'm not going to throw anybody under the bus. I just want to illustrate the issue. So let's say you cared about whether food intake changed fitness. You did an experiment where you either gave high food or low food. And you measure fitness a couple of different ways, say how long they lived, how many offspring they had. And let's say those two measures are strongly correlated. So you feel comfortable a priori using either one as your measure, as your response variable. And let's say you might have measured sex and age as interesting other features of these organisms that you thought might matter. Well, how do you analyze this? Well, at first blush, you might just say, well, let's throw all the data together. Let's ask whether the high food individuals differ from the low food individuals in their fitness. Now, remember, you had two different fitness measures, so you're doing that a couple of times because you might be looking at it for the different measures. And then after you see the data, you might start thinking, oh, wait a minute, there's a good reason to think that in this organism, males should have a bigger effect than females. So let's look at this just in males, or maybe the opposite. Maybe you notice the females had a large effect, and you can tell yourself, you come up with a reason why that might be, and you analyze that. Same for the ones that are old, might have a different relationship between food and fitness and the young ones. And so if you see a pattern in the data, you would be prone to saying, that's a great hypothesis. I can see a reason for that. Let me analyze that. Or alternatively, you might think, oh, I didn't find it a main effect, but I really should have treated sex and age as covariates because those might matter. So let's do the analysis, including them as covariates. Now, so if you did all those different analyses, if you carry through that path of saying, oh, now that I've seen the data, I understand more, I want to do this different analysis, what's the chance of getting at least one type 1 error? It should be 5% per analysis. You should be doing one analysis. So you should have a 5% type 1 error rate. But what is it if you do this process of thinking about the data and looking for different things as you go? Asking really the same question, does food affect fitness? It turns out that if you simulate this, as I just did, the chance of a type 1 error out of that analysis is 40%. There's at least a 40% chance that one of those analyses, which are highly correlated, at least one of those would give you a type 1 error. That would be imminently publishable. You could tell a whole story about why that was true, but it would still be an error. When I simulated this, nothing was true. Everything was the null hypothesis. Okay, let me segue overly quickly to another thing that I've been asked to talk about, and that's publication bias. This is a difference between the results and studies that appear in published sources compared to all the studies that have been done. Here's a simulated example of this, but I'll inform this with data from studies of science. Each dot's a study. Along the x-axis here is the sample size of that study, and the y-axis is the estimated effect size of something from that study. Let's say the truth is about 5%. The null hypothesis is 0. All the ones that I've shown in red here had a p-value less than 0.05. The ones in black did not find a significant difference from the null hypothesis. if you apply a typical amount of publication bias, i.e. that the studies that find something are more likely to be published and the studies that don't find a significant result are less likely, I've applied the estimated filters that we as scientists tend to use in our publication process. And in so doing, it made the published studies have an effect size 3 times larger than the truth in this particular case. A great example of this was illustrated by Rich Palmer in his annual reviews paper in 2000. I'd recommend that everybody go read that. How do I know these numbers about how much publication bias there is? Well, because we don't know what's not published normally. How can we say what are the properties of those unpublished studies? Well, it turns out very cleverly in some fields, we can know about the unpublished studies. And those are fields where we have ethical review of studies before the study is done. So what a variety of studies have done is gone back to ethical review boards, found a list of all the proposals, checked up with the researchers. Did you do the study? What was the result? Did you publish it? Where did you publish it, et cetera? And what they find from those studies consistently is that there's a much larger chance of a study being published if the p-value is less than 0.05 than if it's not. And that's creating this bias in the literature towards the published stuff having more stronger appearing effects than the truth. So 60% more likely of being published. Just parenthetically, it's really interesting to note that this publication bias mainly comes from the behavior of authors, not from the behavior of journals. We as authors blame the journals. It's actually our fault. Another study that's very interesting on this, replicated studies. They took every paper published on psychology and Science and Nature over a period of time, replicated it with greatly enhanced power to do ask the same question, with new data, but with a lot more data. So they would have had 90% power to replicate even an effect size that was only half as large as the original, so much larger than the original studies. And long story short, on average, the effect sizes they estimated from the replicated studies were only half as large as the original, and in about 38% of the cases, it was not statistically significant compared to the null hypothesis of no effect at all. What do we do about this? We have a lot of publication bias. We have a lot of other challenges. Well, science is a community effort. We can make progress through replication with cooperation and open-mindedness toward the mistakes of others and generosity to each other about correcting those mistakes. We should encourage pre-registration of hypotheses. In other words, before we do the study, record in a place that can be accessed later what analyses, what hypotheses you're going to ask with that study so you don't have this harking. We should reward replication of studies from other scientists. We should insist in publications of having effect sizes and not just p-values. We should reward error checking. We should reward people who go and look at other studies to try to verify their results. And we should encourage open science, publishing our data, publishing our analysis code so that we can understand when mistakes have been made and try to replicate in that way. Science works. We learn a lot of things about the world. Science can work even better if we try to address some of these problems. Thanks for your time.